right? So we could go through 1s, 2, 2s2, 2p6, 3s2, 3p, 3. Right? In that filling, what we did, we started at pretty much hydrogen and slowly added electrons until we achieved phosphorized. I don't know. The possessive form of phosphorus, electrons. Okay? The other option is we can use the periodic table as a form of battleship. Phosphorus is in which row? Third row. Which block? Which block? 5 is the... I don't know where 5 comes from, actually. Oh, I see where you're getting from. The block is referencing the sections of the periodic table according to the orbitals. Did we talk about that? S block, P block, D block. Yeah? Which block is phosphorus in? The P block. Which column within the P block? 3. Everything before that has to be filled. So I could just kind of go through and list out everything, and guess what I end up with? The exact same electron configuration as if we slowly went through it stepwise. Okay? So it's one of the things that is nice about this. There's 2 ways to get at that electron configuration. The next part is our valence electrons. What are the valence electrons? The outermost electrons. Okay? The outermost electrons then becomes questionable. What do we define as outermost? What do you got? No?
Wouldn't it be like the farthest energy level?
The farthest energy level. Okay, where is the farthest energy level for phosphorus? I heard a suggestion for P. I heard a suggestion for 3P. Neither of those are the energy level. P is the orbital type. 3P is the specific orbital type at that energy level. 3 is the energy level. So if we're looking for our valence electrons, we're concerned about the highest energy level, which means 3 is what I'm looking at. It's that capital, large 3 out front. Is there another third energy level orbital within this?
Yes.
Right there. Both of those are now in the outermost energy level. Both of those are included in determining my valence electrons. So the valence electrons for phosphorus then become 5. So we could determine the valence electrons by going through and determining the electron configuration for whatever we're doing. Electron configurations can take time. I wish there was a shortcut. Thankfully, there is. As somebody started to notice about the column that phosphorus was located in. What is the name of that column? We could say pnictogens. I don't want the pnictogens. Okay. It is, we look at the number above it. It is 15. We'll come back to the 15 in a second. What's the next thing after the 15? Roman numeral 5, standing for 5 valence electrons. The column title tells you the valence electrons within that column. How many valence electrons does sulfur have? 6. Valence electrons does magnesium have? 2. Okay. Very convenient. It gets pulled directly off the table. It can help us out. Okay. If we take a look at the P block, you'll notice that they aren't all called 3. It goes 13, 14, 15. What is that 10 in front corresponding to? All the D elements. Okay. The D block has how many columns? 10. Subtract 10 from 13 and we get 3. How many valence electrons does boron have? 3. Okay. Subtract 10 from 18. How many valence electrons does krypton have? 8. Okay, so the valence electrons are already embedded on the periodic table. We don't have to do any fancy electron configurations or calculations. It's already there. We just have to write it down. Okay?
However, you do want us doing this process, though.
For what? Why would I want you to do your electron configurations?
Well, to understand it.
If I asked for the electron configuration, guess what I want you to do? Write out the electron configuration. If I ask for the valence electrons,
You still want us to.
I don't care about the electron configurations. It's blatantly told you on the periodic table. You just tell me the number off the periodic table. That level of interpretation is something I can test on. Do you realize it's on the periodic table? If you don't remember that, then you have to go back and do your electron configurations. Does that make sense? Okay. So your textbook has a nice kind of summary slide or summary image of the periodic table divided out into those sections. The first two columns being the S block, then the D block, then the P block, and then our F block. Okay? So by classifying the periodic table or organizing it in this way, we can determine electron configurations very, very quickly. We can determine valence electrons, all of that. Okay? So the periodic table is pretty awesome in that sense for that organization. Okay? So you should remember that classification. I don't really have time for the quiz, so we'll kind of real quickly whip through this. What is a reasonable density for francium? So if we look at that data table, what we would have to do is decide where francium is with regards to those elements. So lithium, sodium, rubidium, cesium are all in the first column, and francium has the symbol FR, happens to be underneath it. What would a reasonable density potentially be? Okay. Last time when we did it, we just said an average. Can we take an average? No, because francium is at the extreme end of it. So what do we have to do? Well, find the pattern. 1 away, lithium versus sodium goes up by 0.4. 1 away, rubidium to cesium goes up by, it's pretty close to 0.4. Right? So francium more than likely is going to be plus 0.4 up. We're looking at 1 point, since you said 2, let's say 8.
2.
Okay.
Sir, your math is terrible.
2.2. 2.2. In the beginning.
I get what you're saying. I'm going to say 2.3 though. Right? You got that? Okay. How many electrons fit in one p orbital? Because somebody already started to mumble it out, I'm going to accept that as our final answer. I heard a 6, and your answer would be wrong. You're not answering the question. What is the question?
In the whole orbital.
How many electrons fit in one p orbital? How many electrons can I fit in any p orbital? 2 and only 2. The question very specifically says 1 p orbital. That means 2 electrons. So let's look at the next question with a quick edit. How many electrons fit in the p orbitals? 6. Okay. Very subtle change in the question. Read your questions very carefully. Answer the question that's asked, not the question you want to answer. Does that make sense? Okay. Why does atomic radius increase down a column? Okay, so for those two, let's actually move to the next slide that shows this. Okay. Our atomic radius increases down a column. Why does it increase down a column? Decrease in the nucleus? Okay, the nucleus gets bigger. What contributes to the size of the atom? Electrons. Okay, if we think back to where the nucleus is, if the nucleus was a marble, the atom size is the superdome. Protons are in that marble. Protons don't contribute to size. Electrons contribute to size. It's really asking volume. Okay, so the nucleus becomes a questionable answer for this. Why does it get bigger as we move from lithium to cesium?
As you add electrons, you add more orbitals.
Okay, we could reference adding more electrons, which I think I started to hear over here. The more electrons answer doesn't work because what happens is we move from lithium to fluorine. We've also increased electrons, but the size got smaller. So we can't just say add more electrons. So Jeremy suggested because we have more orbitals. Well, we still have more orbitals as we move from lithium to boron, right? Okay, we had S and now we have P. So there are more orbitals as we move left to right, and it's still getting smaller. So more orbitals isn't quite right, but getting at the right idea. Say that again? When we move down a column, we're moving into a higher energy level. The higher energy level is further from the nucleus. Right? What happens left to right? So here's my nucleus. There's lithium's outermost electron. Right? I add another electron to become beryllium. Where does that electron go? Up here? It goes to the exact same orbital. Okay? If it goes to the exact same orbital, what happens to the radius? Okay? Don't look at what's up there. Don't look at the answer because we aren't there yet. If I add electrons to the exact same energy level, what happens to the radius? It stays the same. It's going to the exact same place. It doesn't change, doesn't go up, it doesn't go down. It's going to the same step. If it goes to the same step, it doesn't change. Right? And yet, what do we see happening? It gets smaller. So there's another piece that's in there. What's that other piece that's happening? We've also added a proton as we move left to right. So not only are we adding an electron in at the exact same energy level, which means our radius doesn't change, but we're putting in a stronger nucleus. What is that stronger nucleus now doing? Pulling those electrons ever so slightly closer. That's why it gets smaller. Right? So it's all about where our electrons are going within those orbitals and those energy levels. Our size is largely dictated by the energy level. Down a column, we're at a new energy level. Across a row, we're not at a new energy level, so we don't expect a change in size. We get a small change in size because when we move across the row, we're also changing the strength of the nucleus. Okay? When we move down a column, aren't we also changing the strength of the nucleus? Yeah. But again, we're moving the electron to a higher energy level. Okay? It's already further away from the nucleus by moving up. Does that make sense?
Yeah.
Okay. This is where we bring in ionization energy. Ionization energy is the ability to rip an electron away from any atom in its gas state. Okay? So that means when I'm looking at the ionization energy, I pick any atom and I rip an electron away, what charge does that atom become? Positive. It will always be positive. Right? That is what ionization energy is looking at. We're starting with a neutral atom and we become a positive atom. Right? We're looking at the energy required to do that. And I think it's close enough. Let's see if I regret this. Kind of regret it. Okay? We're placing our electrons in, right? We started here with hydrogen. For francium, we'd start up here. For the ionization energy, what are we doing? What did I say I was going to do for? I'm going to take away its electron. How? What am I going to take that electron away to? Not to another orbital, because then I'm not taking it away.
Not to another orbital.
To what?
When it bonds to another atom?
Nope. There's no other atom in play, so it can't be a bond. Well, if there's no other atom at play, that means there's nothing else there.
It loses the electron?
The electron's going to what?
The vacuum?
The vacuum. There's literally nothing else there. That is ionization by definition. Okay? Our vacuum was up at the top. I'm looking at the energy required to rip that electron in francium and move it to just outside its reach. Okay? Or I'm looking at it for hydrogen to move just outside its reach. Which of those is going to have a higher ionization energy? Hydrogen, because? that energy is at a much lower state, much further away from our vacuum. It's going to require a lot of energy to rip it out. Okay? So at a first approximation, our ionization energy is going to track with what? What does our ionization energy track with? What's happening down a column? We're getting bigger. The bigger the atom, what happens to the ionization energy? The smaller the ionization energy. Okay? Because the further away from the nucleus it is, it's easier to push it out into the vacuum. Okay? This works left to right on our periodic table too. Because when we move left to right, we're getting smaller, right? So what should happen to the ionization energy as I move left to right? Okay, it should get bigger. Because it's a smaller radius, it's harder to remove that electron from it. If we take a look at our trend, it increases as we go left to right. Cool, it works. Okay. Anybody have any problems with the trends that are written up there?
Quick question.
Yeah.
The noble gases, don't they have like, their energy, wait, maybe not. I was thinking that their energy levels are like all the way, they have the highest energy levels, like they're filled to the top.
They are full, that doesn't make them higher energy levels. Within an energy level, our noble gases, or the noble gas in that energy level, which is our rho, is fully filled.
Okay.
Yeah.
That doesn't make it easier for the...
No. Sort of. Anybody have any objections to what's written up here? You look at it and be like, oh, that's easy. It's not a big deal. We got some clear outlined rules. Everything looks legit. As a hint, you look at that. Does anything now kind of stand out and be like, oh, wait a second? What does in general mean?
Normally?
Normally, which means there's a not normally. Okay? We could look at exceptions. Okay? And that's usually how people reference them. There are no exceptions to ionization energy. Okay? There are exceptions to trends. There's not exceptions to the ionization energy. And what that's referencing is looking at the electron configurations. We're talking about how we remove an electron from the atom to the vacuum. So if we look at the electron configurations, we can predict which ones should have higher ionization energies than others. Okay, so this is typically what's shown for our ionization energy trends. Okay, so if we go through and take a look, hydrogen to helium. Okay, so each of those points is an element. As I move hydrogen to helium, what happens? The ionization energy did what? Moving hydrogen to helium? It increases. Did that make sense? Well, helium was smaller than hydrogen. Yeah, that actually tracks with the trend. Left to right, it increases. Okay? Lithium to neon, the next set of lines. Okay? Left to right, it increases. Down a column, lithium to sodium. What happens? It decreases. Why would it decrease? Sodium is larger. The gap between that last electron and the vacuum is closer. So the trends are generally nailed down on this. But if we go through and look really carefully at it, okay, a couple things pop out. Number one, all hell breaks loose through the middle of that. The middle of that being our D block. Don't worry about the D block. Okay. Let's pick some simple ones. Let's take a look at this system here, right in the middle. Okay. Our trend increased. We had a weird exception, but I'm going to skip that exception for the moment. It increased. Weird exception. Increased. Okay. So let's evaluate that exception. What elements are we looking at that point? So lithium was 0.1. 0.2 is beryllium. 0.3 is 0.4. Carbon, 0.5. Nitrogen versus oxygen. Why do we see this sudden decrease? Okay. Well, I said the important part was looking at the electron configuration. What's the electron configuration for nitrogen? 1s2. I said electron configuration, not valence. 1s2, 2s2, 2p3, right? For carbon, what do I get?
Carbon is 1s2.
2s2. I don't know why I asked carbon. That was a dumb question. Let's try that again. Oxygen,
1s2, 2s2, 2p4.
right? Well, now it's obvious, right? Okay, well, maybe what we need to do is see what happens when we remove an electron. If I remove an electron, nitrogen becomes 1s2, 2s2, 2p2. Oxygen, 1s2, 2s2, 2p3.
What? Oh, never mind.
Right? Well, now it's obvious. Still no? Okay, well, let's try something else. We need to clear up some space here. Remember when we talked about filling our orbitals? Said we wanted to fill the lowest energy first before we moved up. Okay? So when we filled our 2p's, okay, there were really 3 2p's, right? And so for nitrogen, it's actually 2p1, 2p1, 2p1. We didn't pair them. Why did we not pair them early on? They would repel each other, and I'm at an equal energy with all the other orbitals. So I keep those singly filled, right? What would my electron configuration be when I removed an electron? That's not an eraser. 2p1, 2p1, and I'm going to draw it in for the sake of it, 2p0. Let's do the same thing for oxygen. I have my 3 2p's for oxygen, but I said I had 4 electrons, so it'll be 2p2, 2p1, 2p1. Now I have to pair, right? Okay. What happens when we remove that electron? Right? We remove the paired one first. Well, now it's obvious, right? Remember that whole half-face thing we started talking about? Symmetry is incredibly important. Okay, the more symmetrical that face was, the more attractive they were. Take a look at nitrogen's ground state before we removed an electron. I have 3 2p orbitals. Every single one of those 2p orbitals has a single electron in it. How symmetrical is that? That's pretty perfectly symmetrical. Okay? What did we call, I guess I'm going to be roughly sexist too. I guess we could call a man beautiful too. Okay? Someone that was symmetric we can call beautiful. So I'm going to call that top case for our nitrogen beauty. Right? Beautiful. What happens when we remove that electron from nitrogen?
It's flawed.
Okay, it becomes flawed. It becomes ugly. It becomes a beast. Okay? So nitrogen now. You're nitrogen walking down the street. You are a beauty. Someone walks up and says, hey, I got this stick here. If I hit you with this stick, I can turn you into a beast. You're going to be like, yeah, hit me. Fire me up. Or you're going to be like, no. And you're going to try and avoid getting hit by that stick. Probably going to run away, right? There's a lot of energy to that. Nitrogen does not want to become a beast. It's already starting a beauty. What does that mean happens to its ionization energy? It's going to increase. It's going to require more energy to cause it to become a beast. It doesn't want to become beastly. What happens with oxygen? 2p2, 2p1, 2p1. It starts as a beast. You are now a beast. Someone walks up with their stick and says, I will hit you with my stick and you will no longer be a beast. You will be a beauty because you will be perfectly symmetrical. Yes, you may be like, I don't want to get hit with a stick, but it's worth it. So the energy now gets dropped comparatively. This transition just happens to happen atom by atom. Nitrogen's energy spikes ever so slightly because it doesn't want to become beastly. Oxygen's drops ever so slightly because it doesn't want to be a beast anymore. And what happens? Oh my God, we have an exception. There's no exception. All we're doing is following the electrical fill patterns for our electron configurations and deciding, does the molecule, and it doesn't have a conscience or anything like that, but we're treating it that way, okay, want to do that transition. If it doesn't want to do it, that requires more energy. If it's like, oh, sure, that sounds good to me, that requires less energy. That's our ionization energy. You can apply that logic all the way through for every single pairing within the periodic table and predict your ionization energy values in that respect. Right? Go ahead.
How can we predict which elements are going to be like the beauties and beasts? Like that doesn't show on the periodic table, does it?
It doesn't show on the periodic table. Where it shows is in their electron configurations.
Yeah.
Can you use the periodic table to determine the electron configurations?
Yes.
Yes. So to really see those differentials, you have to have the electron configuration. You would have to write it out.
Yeah.
Okay? Exceptions or nuances within the rules become a lot more difficult to learn and master, which means those types of questions are at that A level and above kind of knowledge. You do not want an A in this class? Don't worry about those exceptions. Worry about the trends. Okay? You will get questions at both levels. Do you understand the trend? Do you understand why we have the trend as it is? Make sense? Okay. I think that's kind of neat, personally. And it was just yesterday that we went through Beauty and the Beast. I thought that was kind of nice.
So you're saying if we,
I usually just had an ugly stick, but
you're saying if we can summarize the trends, we're not at quite the same level as if we can analyze the exceptions and see
Yeah.
the why of the trends?
if you just report, you aren't getting down deep enough in your analysis to deal with getting to that higher level grade. Make sense? The trend is your iceberg. Okay. So, the next thing, your textbook doesn't mention this, so I just want to mention this really briefly in passing. There's also something known as the electron affinity. The electron affinity is the reverse of ionization energy. So in the electron affinity, what I'm doing is now shoving an electron into an atom, which means what happens to the charge of the atom? It becomes negative. It has an extra electron. Okay? We have similar trends and sit-ups that we can run through and explain, but it isn't a big deal to evaluate it. So don't stress about the electron affinity. Okay? Which then gets to the why. Why mention both ionization and electron affinity? Well, that really addresses this next slide, electronegativity. Depending on how electronegativity is measured or defined or quantified, one of those accepted quantifications is taking an average of the ionization energy and the electron affinity. Okay? Ionization energy is the ability to remove an electron. Electron affinity is the ability to shove an electron in from vacuum. Electronegativity is now saying, let's look at the ability for the electron to move, but I'm going to very specifically look at bonding electrons located between two atoms. What is the ability of any one atom to take the electrons from that bond? The higher the number, the more electronegative the element is, okay? And the more willing it is to steal electrons. Fluorine is the most electronegative, cesium is the least. Okay? This trends opposite metallic character. Okay? So if you happen to know your metallic character, you know electronegativity. Again, this is a trend. It is not a perfect relationship, but it works out for the most part. Okay? Any questions about electronegativity that might have been bothering you from, say, the Lewis video? Really?
Remember those questions really got me.
The very second question on the exam, on that Lewis video, asked what?
They wanted us to write the elements on the electronegativity. I think
What elements were they?
Nitrogen, sulfur, and bromine.
Bromine, sulfur, and nitrogen. Okay?
Oh, yeah.
This is a nasty question. This question is intentionally designed to trip you up so that when I ask, do you have questions, you come to class and be like, yes, I have a question. You asked me this question. I have no idea how you got that answer. Okay? Oddly enough, it seems like most people actually get the answer right, but I think the reason you got that answer right was that you looked at the table to come up with the answer. How many of you want to memorize the electronegativities for any of the elements? No. Okay, so nobody wants to do that. Well, is it on the periodic table? Okay. Fluorine is 4. Where for fluorine do we see 4 on the periodic table? Not anywhere. The electronegativities are not on the periodic table. So all I want you to do with electronegativities is memorize the trend behind it. Okay? So if we ignore the exact values, which we can't see because the slides are kind of messy right here, how do we determine the trend or which one is more electronegative than the other? Well, our trends are based off of column and row. Are any of those elements in the same column?
No.
Are any of them in the same row? No. So what we have to do is find something that they have in common and evaluate and compare to that thing. So let's take a look at sulfur and bromine. What do they both have in common that we could use to evaluate their electronegativities? That might be kind of a weird statement. It has to do with the periodic table. There are 2 things they have in common. 2 elements they have in common. One begins with C, the other one begins with S. Chlorine is one, yes. And the other one is selenium. Okay? Those 2 elements we could use to try to determine which of those 2, sulfur or bromine, is more electronegative. So let's go through and figure that out. Let's start with bromine and chlorine. Okay? So there's chlorine, there's bromine. I'm trying to decide which one's more electronegative. So I go to my trends. According to my trends, as I move up a column, well, bromine and chlorine are in the same column, I become more electronegative. So which one's more electronegative? Chlorine is greater than bromine. Good? Okay. So now let's move to sulfur. So chlorine versus sulfur. According to the trends, which one's more electronegative? Chlorine. Cool. I found something that's in common. I've now got that relationship. Where is bromine with respect to sulfur as far as electronegativity? They're both less than chlorine. But the question is to rank bromine and chlorine and sulfur. Can you rank them? Not with that data. We do not have the data to be able to rank those according to the trend. The question I asked was intentionally obnoxious because you will never see that question. I cannot ask that question and expect you to use the trends. You would have to look them up. How can I change the question so that you would be able to answer it based off of the trends? I could give you the electronegativities, but that's kind of silly because I'm pretty sure that you could tell me 1 was smaller than 2 was smaller than 3. How about sulfur, arsenic, and fluorine?
That's fair.
If I run the opposite diagonal, I will actually be able to rank those. Okay? That is fully expected. I believe I also asked that question so that you had both types in that practice. Okay? Electronegativity is probably the single most important topic in chemistry, and it just does not get discussed that much. Okay? Super, super important. It explains all bonding, all intermolecular forces, boiling points, melting points, vapor pressures. Okay? Whether 2 things mix with each other, all comes back to understanding electronegativity. Okay? So electronegativity is super, super important. That trend is critical to memorize, okay? In my opinion, at least. Okay. Our chapter 4 summary, some people like the summaries on it, so here's the summary of all the scientists and all the big things that come out of it. Chapter 5, same deal, all the big thing that comes out of it. The one thing that isn't mentioned, or that we haven't talked about yet because I'm pushing it to the next unit, is ionic charges. So we'll just erase that off that slide. Okay. The rest of that we've talked about in depth. You should be able to answer any question about those topics. There's our electronegativity again. And now what we shift into is our types of bonds and ultimately Lewis structure. Okay. I am really, really nitpicky when it comes to Lewis structure. Okay. There are multiple ways to solve for the official Lewis structure. Okay. All of them get the answer. That does not mean your understanding of how you got to the answer was correct. Okay. I can flip a quarter up in the air and you can call heads and be like, oh, why'd you call heads? And you say, well, it landed heads 5 times before that. Completely irrelevant. Okay? It's random luck of the odds. Okay? Same kind of thing is happening with Lewis structure, but at a much more deep, complex level. Okay? If you follow what the textbook says, or probably what your high school instructor said, or probably what any other general chemistry instructor says on this campus or any other campus that I have ever seen a general chemistry instructor talk about Lewis models, you will screw yourself over when you move to OChem. Okay? Because it is a very subtle change in how you approach the question. Okay? That's the part we need to address. So, types of bonds. We start off by saying we have ionic and covalent. Ionic are metals and nonmetals. Covalent are 2 nonmetals. Okay? Lewis structure is all about the nonmetals. So we'll keep our focus there for the rest of this unit, which is why we're going to end up skipping pretty much the next couple of slides. Ionic bonds, we've got charges. Well, I just said we're going to ignore ionic charges for this unit. Okay, so we're skipping that. Okay? Ionic radii, well, that's still looking about charged ions, so we're skipping that. Okay? Covalent bonds, this is actually kind of important. When we look at a covalent bond, we're looking at sharing electrons between those 2 atoms. Okay? So what we're referencing is the bond length. Okay? When I look at the bond length, what would I expect it to be? So it's the distance between the nuclei. Should it just be the sum of the radii of the original nuclei? Right? I just bring 2 atoms near each other where their outermost radii touch, and that's now the distance between the 2 nuclei. No. For us to have a covalent bond, we have to be sharing electrons, which means the outermost orbitals have to overlap, which then means the distance between the nuclei gets a little bit smaller than the radii summed. Kind of make sense? Yeah. That's really all I want you to get out of your bond lengths, right? At least as far as covalent. After that, we've got bond energy. I promise I will come back to bond energy because it's kind of an interesting topic to talk about, but I don't want to talk about it for this unit. And this is really the meat of what I wanted to get through today, our Lewis structures. Right, and the rules behind it. I've got 7 rules. Okay? These rules are not the same as your textbook. They are not the same as you will find in pretty much any other external source. Okay? They, interestingly enough, are identical to the rules the Tutor Center has printed on a worksheet for you. That's because I wrote those rules, and I insisted the tutors use those rules because I don't want them screwing students over, ultimately forgetting into my class in OChem. Yes? It is the same from last night's video as well. Okay? Because I did that too. Okay? So, it sounds like me? Yeah, that's good. It was. Valence electrons, it might have been at like 3 in the morning. So rule 1, total your valence electrons. Rule 2, we want a center atom. Okay, that needs to connect out to everything around it. Okay? That is typically the least electronegative atom. Okay? Why would I put the least electronegative atom in the middle? What did electronegativity measure?
Its willingness
The willingness to steal bonding electrons. If I put the most electronegative atom in the middle, it's going to take all the bonding electrons, and we don't have any bonds. Okay? So our most electronegative are typically on the outside. There are exceptions. Anything that cannot bridge. A center atom must be able to reach out to other atoms. Right? That's the whole point of being in the center. So hydrogen can never be a center atom because hydrogen is very, very small. It can only have 2 electrons around it. If we look at its electron configuration, it was 1s1. How many more electrons can fit into that energy level? 1. So we get a maximum of 2 for hydrogen. Okay? We'll then add electrons, and this is the rule that stands out the biggest. Add electrons in pairs to the most electronegative atom to satisfy the octet. Okay? This is also known as the Noble rule. When we're looking at Lewis theory, he picked small atoms to work with his bonding theory. So we're looking ultimately at anything bonding within the first 2 rows. How many electrons fit in the second row? Or the second energy level of our periodic table? 8 electrons. If we turned that into a formalized notation that we could then always remember that, we might call that an octet. That's the reason behind the octet. Okay? Because it comes to the second energy level holding 8 electrons. Okay? What did we say we did about the transition elements? Because those showed up at the third energy level, right? And what did we typically do with our transition elements? At least for this class. But we ignore them, which means even when I move to the third energy level, what can I do? I can ignore the transition elements. How many electrons would I have? 8 again. Okay? So it's our octet rule. Apply the octet rule always, and you'll be okay. Right? Continue adding electrons to the rest of the atoms until we've achieved the total electrons from step 1. The whole point of step 1 was to get all of our electrons pooled. We then dump those electrons into our structure according to where we would expect them to disperse, i.e. placing them on the most electronegative. Okay? This is different from how the textbook explains it. Okay? And the reason being is ultimately Rule 6 is why I have that difference. The textbook says go through and build your atom electron configurations, and then you'd be like, oh, look, they're like Legos. You can put them together. You're not toddlers. We don't use that rule. Okay? These aren't Legos. The electrons freely move across all of the atoms. They will disperse according to their natural tendencies. Okay? So there's none of this Lego crap that the textbook is trying to put out there. I understand what they're trying to go for, but we're a little bit more advanced than that. Okay? Even in high school, you should be more advanced than that. Why then do general chemists tend to teach this stupid Lego rule? It's easier for them to achieve one structure. The reason I dislike it is then when you move to Rule 6, you're like, well, what the hell is that? I have no idea what to do. Because you don't have the fundamentals to allow you to see what's happening with Rule 6. Okay? So it's super, super important that we follow Rule 3. Okay? Convert pairs of electrons between atoms into a line to represent a bond. We're only looking at pairs of electrons between atoms. If the electrons are not between atoms, don't turn it into a line. Okay? I get in trouble for this. I said really bad things yesterday, and I realized later I could rephrase it. Okay? The only reason we have chemists that are still drawing pairs of electrons, all pairs of electrons as lines, is because that's how they were traditionally taught, again, from Lewis model, which was based off of a cube showing lines as the face of a square. And so they said, oh, I had all the faces of the square, so it was okay. Okay? The issue with that model is it does not differentiate between bonding electrons and non-bonding electrons, which means when we move into more advanced topics like shape, we have to add a layer of interpretation that we shouldn't have to do. So the only time you see those lines drawn on for all pairs of electrons is because the person that's talking about it is either insanely old or was trained by someone insanely old and nitpicky as all hell. Okay? Hopefully, and this is where I'll modify the language, those people will retire, and then the part, that was the modified part. The not modified part was, or die. And we will stop doing this stupid line thing. Okay? Lines are for bonds. Dots are for not bonds. Okay? After that, you will move electrons, move non-bonding pairs of electrons. I won't touch bonds because they're already occupied. They're already doing something. I will move them around until I've satisfied the octet for all atoms. Okay? If there were multiple electrons, choices of electrons that I could move, that means I have multiple structures I have to draw. That concept is resonance. Okay? The last one is assigning all non-zero formal charges in the upper right-hand corner. In the video, you watched a more drawn-out version of formal charge that is responsible for 151 and above. Okay? For 130, you do not need to worry about calculating formal charge. All you need to do is say what it is in the upper right-hand corner, and you're done. Okay? The next big part before we look at examples, shape summary. Okay, when we look at our shape summary, this is it. This is how you interpret it. There is no simpler version of this. Okay? And I know you might say, well, isn't there duplication? No. Actually, there's not. The linear here is different from the linear up there. They both say linear. That's true, but they're applying to inherently different things. The first line is A bonded to B. The second line is A bonded to two B's in a straight line. Okay? Those are different shapes. Okay? So we have to be able to interpret off of what's up there to come to our answers. So let's pick a good example for this. If we were to go through and do, say, water with a formula of H2O. Okay, we'll whip through this one really fast. Oxygen has 6 valence electrons. Hydrogen has 1. There's 2 hydrogens, so there's 8 total valence. Hydrogen can't be the center atom because it can't bridge, so oxygen is my center atom. I will scatter the hydrogens wherever I feel like around the oxygen. I will now place my 8 electrons into my structure, starting with the oxygen because the oxygen is more electronegative. Anywhere I have a pair of electrons between atoms, I will convert them into a line, and I now have the Lewis structure for water. What does the shape for water look like? Linear. Is it linear? No. Lewis structure does not apply shape. Shape comes from the Vesper model that's using this summary. So when we go through to apply, how does that work? Okay. This again goes back to kind of the origins of Lewis. Lewis was based off of cubes, so we'll base it off of a square around the center atom. Are there electrons on the upper face of that cube? Square, sorry. Right face? Yes. Bottom face? Yes. Left face? Right face? Left? Bottom? Front? Just checking. How many faces of electrons? 4. That means I go to my electron groups. I have the tetrahedral electron group geometry. Okay, that's the answer for water. But didn't we say water was bent? We even came up with linear as a potential option. Neither of those are tetrahedral. So that's kind of weird. Okay, well, let's further address what's happening within water. Are all of the groups of electrons there the same?
No.
No. How do we know that?
You can see the bonds on the electrons.
Because I drew my non-bonding electrons as dots and my bonds as lines. I now know that there's 2 different types of electrons. This is why we do that. Right? So we look at that and we say, okay, well, there's two groups or two faces that are non-bonding electrons. There's also two faces that are bonding. Right now, all I have to do is look in the tetrahedral section. I will not look anywhere else. So two are bonding, two are non-bonding. The shape, bent. Okay, kind of makes sense?
Yeah.
Okay. And I apologize for this, because it's kind of a loaded question. You sent me an email or you had a comment about this. Can you clarify that?
So, you asked a question on, you gave us the Lewis structure of an atom and, or a bond, and you asked us what it was, and I put tetrahedral, but I did not put bent on it, I believe.
Mm-hmm.
And I just wanted it to be clarified, like in possibly like that chart. Like if we were to take an exam, which we are next week, we have the periodic table, but we do not have a table such as that.
Yeah.
And we must memorize every single shape.
Yeah.
And the bonds.
Yep. You have to know all of those shapes. Okay. If you go to the tutoring center, they have this image with a whole bunch more after it. Because, believe it or not, we can exceed the octet for certain elements, and we can go up to 5 groups and 6 groups of electrons. That's going to introduce a whole nother triage, I don't think triage is right, but a whole nother tree of shapes. Okay? That's useful for 151. We're not in 151, so I don't care. If you use that, cross that part out, you're up in this section. Okay? Some other simplifications. We're usually concerned about octets, right? Okay? If we have octets, how many groups of electrons would we have? Groups of electrons. 4, because each group comes in as 2 electrons. Which means on this table, really the only part that's super important to memorize, the last, whatever that is, 4 rows for tetrahedral. That section is super important. Much less so trigonal planar, but sometimes that gets thrown in. Okay? Or even further less so the linear shapes for the top 2, because if you have just 2 groups of electrons, what is your shape? Linear. Either any way you slice it, it's linear. If you have only 1 group of electrons, any way you slice it, it's linear. So you can pretty much ignore the top 2 sections. They're only there as kind of factual. That would be the answer. Right? Does that make sense? Okay. Yes, you do have to memorize a little bit more. It's not that much more, unfortunately, is the best answer I can give you on that.
But for some of these, if you break the words down onto the morphological level, like tetra, tri, planar versus pyramidal, like if you can pull the language apart, you can piece this back together based on what the pieces mean. Tri versus tetra.
And because I actually want to get into some more examples, what we're going to do is go ahead and skip on this. Unfortunately, I will pick an example where we can come back and apply the shape to it. Right? So, sorry?
When you are doing, during the process when you are trying to do the dots,
Yes.
is there a particular pattern you have to follow?
Is there a path that you need to follow for drawing a Lewis structure, for assigning the dots? Yes. Is there a path for how you go through and draw Lewis structures? Yes. This is the path. Okay. This path has an awesome way to continue on. Every other path ends at a cliff and kills you. Man. Okay. Ends at a wall that hurts when you run into it. This path continues forwards. That's why I recommend this path. Okay? If you talk to the tutors, any tutor that has had me as a student has had me yell at them probably on multiple occasions about Lewis structure. Okay? So you can commiserate about how much I'm yelling about it. Okay? It's super important. Follow this path. Okay? So let's take a look at some examples. Okay. I didn't think I had done all 4 of those in the video, but apparently I had. I'd intended to leave some for lecture. I apologize for that. Is there any one of those 3 that you're like, I need help with that one? Or 2?
Should we go over them again?
Okay. We've got our first example of NH4. And then we'll do one similar to both of these, but different. Right? So NH4. So to start it up, total of valence electrons. So step number 1, nitrogen has how many valence? Well, it was 1s2, 2s2, 2p3. Oh, 5 because it's in the 5th column. Hydrogen has 1 valence electron, so I add it up and I get 6. No? Why not?
4 hydrogens.
Okay. There were 4 hydrogens, so I can either add 1 for each and every single one of those hydrogens or multiply it by 4. Now I add it up and I get 9. Okay. What does that positive mean in the upper right-hand corner? Okay. Remember, the upper right-hand corner is where we specify information about the electrons. Okay. Electrons aren't positive, but remember, electrons aren't the only thing that contribute to charge. Protons do also. Okay. If I was neutral, it would be 5 and 4, and I'd be perfect. But this says positive. How do I become positive? I have to take away an electron. I can't adjust the protons. I have to adjust the electrons. So what I would do is add an extra thing down here saying charge as my additional thing to take into consideration here. Because I am now removing an electron, I will subtract 1. Which is kind of weird, right? I'm subtracting 1 and yet I'm positive. Why?
You're taking away the negative.
Electrons are negatively charged. I'm taking away a negative. Right? If you lose debt, that's a good thing. Right? You're becoming positive. Right? Same thing is happening here. The minus sign is something that is a horrible thing that will plague you through your entire science career. Okay? You have to watch out for it. Okay? So 5 plus 4 minus 1 gets me.
Why is it just minus 1 though? You're only taking away.
Why am I only taking away 1 electron and not, say, 2? What's the size of that positive?
1.
It's an implied plus 1. If it was a plus 2, then what would I have to do? Take away 2 electrons. Right? And believe it or not, we will kind of come back to that question with another example. Okay, so far so good? Center atom. Right? Why is it nitrogen? Nitrogen's more electronegative than hydrogen. Hydrogen can't bridge, so nitrogen has to be the center. I will then scatter my hydrogen atoms around the nitrogen. Okay? Those can be going completely arbitrary. For organization's sake, remember the origins of Lewis. Lewis is based off of a square. Place the hydrogens on the face of a square. Does it matter where I place them on that face? Okay, why not? What's my name? What's my name now? Even though you're seeing a different part of me, my name should have theoretically stayed the same. Okay? The same thing is happening with our Lewis structures. We can spin or rotate that, but the character is still staying the same. Still the same compound. Okay? Add electrons to the most electronegative. Which one's the most electronegative? That would be correct. So now we have 4 hydrogens. Always good to check your work. Now that we have 4 hydrogens, we need to add our electrons to the most electronegative. Which one's the most electronegative? The nitrogen. 2, 4, 6, 8. How many electrons am I allowed to put in? 8. So I can't put in any more electrons. I can move to the next step. Any place I have a pair of electrons, I will turn into a line as long as it's between atoms.
All of them.
Line, 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 line. So far, so good? Satisfy octet. What is the octet for nitrogen?
8.
Nitrogen?
8, sorry.
8. So I would go around and check. Well, there's 2 electrons there, 2 there, 2 there, and 2 there. So I've got 8 electrons around the nitrogen, right? How many electrons do I have around the hydrogen?
2.
I also have 2. Notice I'm counting the pairs of electrons twice. Why can I do that? They're shared. Those electrons are equally between both atoms. So both atoms get access to that count. Okay? So my octets are satisfied. What do I have to do about 6? Nothing. I don't have to move any electrons. Okay? The last part, I've got to strike through on it because that's how you would actually calculate formal charge, which unfortunately you were forced to watch. I apologize. Okay? Don't stress about that. What you guys are responsible for is acknowledging that there is a charge on the molecule. Where do we specify charge? The upper right-hand corner. So I will put a plus sign. Because that is now a charge, I want to differentiate it from the mathematical operation. You'll typically see me put a circle around it. Okay? I also want to make sure that that positive charge is associated with that structure. So theoretically, I should include brackets. There's a final answer that is correct. Okay? I am also inherently lazy, so here's one shortcut that you might see. That is not 7 plus. That is the corner of a bracket that I got tired of drawing and then wrote the plus next to. Both of those are acceptable as far as I'm concerned. Does that make sense? Okay. So now let's level up. We're going to do a mixture of both those two and even bring in the aspect that Lauren was asking about. I want the Lewis structure for CO3 minus 2. Did I do that one in the video? Good. CO3 minus 2. How many electrons does carbon have? Sorry, valence electrons.
4.
4. Oxygen.
6.
6. How many oxygens?
3.
What is the charge?
-2.
The charge was -2. What do I do? I have to add 2 now because it's negatively charged. I add 2 because it says -2. So my total here, 24. Center atom. Carbon. Blue's a bad color. We'll put our oxygens scattered around the faces of a square. I will now draw in my electrons, starting with not carbon,
Oxygen.
the oxygen. Oxygen is more electronegative than carbon. 2, 3, 4, 5, 6, 7, 8. Can I get a snap with that too?
What?
Thank you. How many electrons have I drawn in? I should have 24. I will convert pairs into a line. Whoops. I wrote it really small, so I end up erasing more than I wanted to. There's a line, there's a line, there's a line, which I'm about to erase again. Okay, I think I just heard an uh-oh. What's the uh-oh? Rule 6, satisfy the octet by moving pairs. Carbon does not have its octet. So what do I have to do? Move electrons, okay, to satisfy the octet. The 2 ways that students screw this up. Way number 1, cool, carbon has its octet. Okay. The problem is I'm not at 24, now I'm at 26. Can't do that. Okay. Step number 2, I'm going to take those electrons from the oxygen. Cool, carbon has its octet. Now oxygen is messed up. So I have to move that pair of electrons from the oxygen in such a way that both the oxygen and the carbon have access to them. I will move them to the space between, which then turns it into a line. I now have, as some of you have pointed out, a double bond. Right? Did I have to take that pair of electrons from the topmost oxygen? No. Could I have taken it from the side? Yeah. Would that look like a different structure? Yeah. We can make funny faces about that. Yeah, it does. Bottom one, yeah. There are 3 answers that you have to draw for this. That is resonance. If you follow what the textbook does, you end maybe at this answer, and then you're like, well, then what do I do from there? I must be done. Nope, you missed the other 2 structures. If you follow it the way I described it, you naturally find that you have resonance based off of where those electrons aren't placed. Okay? It has a logic behind it. Okay? Last couple parts, I know I'm out of time. Officially, we'd have to draw the brackets, and -2 in the upper right-hand corner. Okay? But here's where I really wanted to get to. I promise this one's actually kind of important. Back to the shape summary. What is the shape? So when we're asking shape, we should always be referencing the center atom. Sometimes it's obvious, sometimes it's not. On the test, I try to bold the center atom so that you know what I'm talking about. Okay? What is the shape for that center atom? Both electron geometry and molecular geometry. T shape, right? It looks kind of like a sideways T. Wrong. Our rules for deciding shape. Check each face. Are there electrons on the left face? Are there electrons on the bottom face? Electrons on the right face? Electrons on the top face? Yes. I have how many groups of electrons? 3 groups of electrons, which means my shape is trigonal planar. For my molecular geometry, so that was my, we'll say that's electron geometry. The molecular geometry says how many bonding or non-bonding groups. Well, do I have any non-bonding groups?
No.
On the center atom, I have to see just a pair of electrons. There is no non-bonding pair of groups. That means by definition, I have how many bonding groups? 3. Remember that flow chart. It has to come in at 3. Where you might be calling question is, aren't there 4?
Yeah, double.
Those electrons are occupying the same face. That counts as 1 group. Only when they're in a different face can they count as a unique group. Okay? So the shape for molecular geometry is trigonal planar. I apologize for talking too long. Please hold on just a second. Again. Don't go. Stay. Okay, there we go. This slide, super, super important. This should just, as soon as I say go on the test, after we do like the name swap, this is what you should be writing on the test. Something to this extent. Because you have a periodic table, what you should be doing is transferring this. Number 1, the Roman numerals. Right? Get that information written as your valence electrons. So if you get a question later on in the test, you don't go, oh, what was valence? I don't remember. I'm going to say it's 16. Okay? If you've identified it on your periodic table, you no longer have to think about it. You just look at the periodic table. The next part, we talked about electronegativity. It increases up and to the right, fluorine being the most electronegative. I've got that color-coded in blue. You could just kind of draw arrows. Red, ionization energy, it increases up the column, it increases left to right. And then atomic radius increases down and increases to the left. Right? If that information gets drawn on, you've got kind of a guaranteed 4 or 5 multiple choice right off the bat, as long as you drew that on correctly. Okay, and with that,